Hello guys, and welcome to this lesson number 3 on the series of on calculus. In this series, in this lesson we will summarize the first principle, and I hope to take just about 2 minutes to summarize it, and then we'll start looking at the derivatives of algebraic functions. We will start with x power 2, then maybe x power 3. I'll give you a chance to try x power 4 for yourself, and then we'll find the general derivative for x power n. Okay? If time permits, then we will try and generalize for algebraic functions. Okay? My name is Solomon Saduma, and if you are new to Elimika, please consider subscribing and hitting the notification bell so that you are notified whenever we make a new video. All right? Okay, let's begin now. So in summary of what we've done in lesson 1 and 2 was what it means to find the derivative of a function using the first principle. So effectively what we have said is that the gradient or the slope of a straight line is always constant. So if we're given a straight line such as this, then we know that the gradient is constant everywhere along the line. It doesn't matter. You pick any 2 points on this line and try to look for the gradient, you should get the same value, right? Those 2 points could be within this circular region, which will be our point, or it could be between the ends of that circular region. Whatever you do, the gradient is going to be the same. So a linear function or a straight line graph will always have the same gradient. On the other hand, a curved line such as what we have here, so of course to find the gradient of the straight line, it would be the change in y over change in x, which we already know, y2 minus y1 over x2 minus x1. That should not be a big deal, we already know that. On the other hand, if we had a cubic function which is a curved line such as this one, then it becomes ridiculous to think about finding the gradient around this circular region. It becomes difficult to find the gradient along this path because the gradient is different at every point. Okay? So we cannot find the gradient of a curved line from say this point to that point. All right? And therefore, what happens if we wanted to find the gradient of such a line? We can only find the gradient at a fixed point. So if we were given a curve like this, it is difficult to find the gradient. We can't talk of finding the gradient of the whole line, but we can think of finding the gradient at some point inside the line. So for example, if I zoomed in like that to a very specific point on that curve, so I have a very small point there, I'm going to call that point P, then it is possible to find the gradient. It would be reasonable to talk about the gradient of that point, and that's because if we take a small region like that, the line that is represented inside that point is relatively free. Let's zoom into that point, and you can see that when we get close into that point, we have almost a straight line. In this case, now it is possible to find, the change in x and the change in y, and then we can use this formula here to find the gradient of the line. All right? And if delta x is very, very small, remember the point we are talking about here was this, and if we make it very, very small like that, so that the diameter of that circle is very, very tiny, so delta x is very, very small. If we can do that, then the gradient that we get, so if x is made very, very small and very close to 0, then the gradient that we get for that line becomes the true gradient, or very, very close to the gradient, and we can find that gradient using this formula. When we find that gradient, when the value of delta x is becoming very, very small, approaching 0, then the gradient we find is called the derivative of the function, which is this line here, the derivative of that function at the point P. So this becomes the derivative, and that is the small summary of what we mean by differentiation from first principle. So in fact, this is what we refer to as the principle of differentiation, right? So to differentiate from first principle, we need to find the true gradient by taking an approximation of the gradient using this symbol. So this is the summary of differentiation, or looking for the derivative of a function using the first principle. Now let's try and use this formula so that we understand. Let's try and use it to find the derivative of the function y is x squared. Okay, let's start with that now. All right, so here is how a question might be brought to you. This is true for SL as well as HL students. So the question here is, use the method of first principles to find the derivative of the function y is x squared, or f of x is x squared. All right, so if you meet a question like this, how do you start? What you need to remember is that you're going to pick a random point on a curve. So let's draw a line. So this is the graph of y is x squared, looks a bit like this, but we don't need to know how the graph looks like. It doesn't matter, we only need to pick a point on a line. So I could have drawn any line here and it would work just fine. And then what we need to do is to pick a point on that line, let's call it point P, and look for the x coordinate and the y coordinate for that point. Now if we zoom into that point, that is equivalent to zooming into the point that we did just earlier, then it is possible to pick a second point. So we have a point A in the line and another point B, and we can find the coordinates of point B. If we let this distance here be delta x, then we can find the coordinate of the x coordinate of point B there, and consequently the y coordinate of point B. And because the function is f of x is x squared, that means f of x is x squared, but f of x plus delta x is going to be f of x plus delta x, which is x plus delta x squared. All right, let's see if you understand this. All right, so if I had 2 here, then what we would have here, suppose this, the coordinate of this point was 2, then the y coordinate there would be f of 2, which is actually 2 squared according to this formula here, and that would be 4. So in the same way, if this is x plus delta x, then the y coordinate has to be x plus delta x squared, because that is what we are feeding into the position of x squared. All right? Right, let's move on. And so, knowing this, we can replace this information into the formula for in the first principle. We can replace that formula. Let's see. So that's the formula we are talking about. And so y2 minus y1, our y2 is x plus delta x squared, and our y1 there is x squared. This is our x2 and that's our x1. So if we substitute into the formula, we're going to find the derivative using that formula. And let's start. So I've replaced y2 and y1, and x2 minus x1 leaves us only with delta x. So this is what takes the place of that, and this is the formula we'll be using to determine the derivative from first principle for any function at all. And so here we are. The next thing we need to do is to open this bracket. If you open the bracket there, that's a binomial expansion, or power of 2. We get x squared plus 2x delta x plus delta x squared. So we have that there. If you like, you can put this in brackets. This here should be in bracket because we are saying it's the whole delta x being squared. All right? And then we have that. The next thing, of course, is this term and this term here are going to cancel, and if we cancel those two terms, we are left with 2x delta x plus delta x squared, everything over delta x. Now directly I can put 2x, I can put this as 2x delta x over delta x, in which case delta x and delta x cancel. I'm left with 2x for this term, and this becomes delta x squared over x, which becomes over delta x, which becomes delta x. And so it's easy to just write 2x plus delta x, but for the sake of students who will be studying also differentiation of implicit function, I'm going to leave this as delta x over x to remind you of something when the time comes. All right, and so this function becomes, this expression becomes 2x delta x, because we have cancelled those two, the first two terms there. So we are left with, let me just go back a little. So because this disappears and that disappears, we are left with the middle section. So that becomes 2x delta x plus delta x squared, everything divided by delta x, all right? Now this divides that, and we have 2x, and this divides this, and we have delta x, but I'm going to write this like that so that we keep this in mind, all right? So delta x divided by delta x is of course 1, but I want to leave this here for the moment to remind you where this is. So when we get into implicit differentiation, you will understand why when we are differentiating y, we will always remain with a delta y over delta x, but that will come later. Please just remember that point. Anyway, if we now feed this into that equation there, we say that the true gradient is the limit as delta x tends to 0 of this function here. Now, of course, this becomes 1. It doesn't matter how small delta x is. Delta x divided by delta x is always 1. So this will cancel out, and we are left with 2x. On the other hand, as delta x tends to 0, this term here becomes 0, and so we are going to be left with, if we bring in the limit operator, then we are going to be left only with 2x, which is to suggest that if y is x squared, then dy by dx, or the derivative function, is going to be 2x. Okay, so we have just found the derivative of x squared using a method of first principle. Okay, all right. So let me summarize this. So if a function is given as y is x squared, then the result dy by dx, which is equal to 2x, is referred to as the derivative of this function, or also called the derived function of the function y is x squared. And a better term that you may want to use is that this is called the gradient function. And it's called the gradient function because the derivative function is used to determine the gradient at any point on the line, provided we know the x coordinate at that point. For example, if we went to the line y is x squared, then the derivative at the point where x is 1, if we want to find the derivative at x is 1, we put 1 in the derivative function or in the gradient function, and that tells me the gradient there is going to be 2. If I want to know the gradient at the point where x is 5, I put 5 into the gradient function, and I'll find that the gradient there is going to be 10, and so on. Okay? All right. The second point is that the process of coming from the function to the derived function or to the gradient function, this process, or the process we've just followed, is referred to as differentiation. Okay? So differentiation is the process of determining the derived function or determining the derivative from a function. The derivative is the gradient function. Differentiation is the process of finding the derivative. Okay? In utility, that is, why do we need to know this? Well, as I've just said, that the gradient function can be used to determine the gradient of a line at any point. If we know the x coordinate of the point, we will be able to find the gradient. Okay? But that's on a simple graph of y equal, a graph of y versus x. But what about in real life scenario? Where does this become useful? Okay? Calculations involving velocity. By definition, the velocity of motion refers to the rate at which the distance or the displacement of an object is changing. So this is about rate of change. So gradient is about rate of change. So if we were looking at how the distance traveled by an object, correct word to use there is actually displacement. If you wanted to see how displacement of an object changes with time, we will call that the rate of change of displacement, and that is called velocity. Similarly, acceleration is the rate of change of velocity itself. So a car is accelerating at 5 meters per second squared. That would be the rate of change. That would be the gradient in a velocity versus time graph. Fuel consumption rate. You may have a car that takes up 6 liters per 100 kilometers. Some will use 12 liters per 100 kilometers and so on. So the consumption rate of a car refers to how many gallons or how many liters of fuel it uses for every mile or for every kilometer it travels. So that would be referred to as a rate of change. Volume flow rate would be referring to the volume at which a liquid or a fluid flows in a pipe, water in a river, and so on. The picture you see there is of a Formula One car being refueled in the days when refueling was taking place. In those days, a Formula One car would be refueled, would take in about 12 liters per second. That means if you have a 55 liter SUV, that would fill up in less than 5 seconds. I know that I take more than 2 minutes, perhaps 4 minutes trying to fill up the gas tank. All right. Here is the Niagara Falls. Data shows that the volume of water that flows through the Niagara Falls is about 2,407 meters cubed every second. So this would be referred to as volume flow rate. In the case of the Formula One car being refueled, the rate at which volume of fuel goes in is 12 liters of fuel going into the tank every second, right? So here are some practical examples of rates of flow. Okay, volume flow rate is a rate of flow. The rate of electrical energy consumption, which is what we refer to as power. How much energy, how much electrical energy do you use every second in your household? That would be a rate of change for electricity. There are other examples, force being the rate of change of momentum of a body. There are things like breathing rate. If you've been running, then you tend to breathe in and out a little more frequently than if you are seated. There is rate of reaction. In a chemical reaction, sometimes chemical reactions occur faster than others. There is what we call radioactive decay rate. All right. The reason why I'm talking about these things is for you to, you may want to know this when it comes to your math IA or the mathematics exploration. You could go about it in any of these areas, and just remember that when you go into stuff like this, you're thinking about rates of change, which come into calculus proper. All right. The diagram you see there is what happened is a satellite image of radioactive levels in Europe from the Chernobyl nuclear disaster. This was the first 8 days. If you look at the data there, it's showing the first 8 days of after the accident, right? And you can see how the radiation spread across Europe. All right. So that is related to radioactive decay, which is what takes place at the Chernobyl facility. All right. One more thing is unemployment rate. This is in the topics related to economics. Rate of return, interest rate, birth rate, and heart rate. And I think I have a diagram there showing someone's heart rate there. This is somebody obviously running. So the heart rate is quite fast. If this person is seated, it's probably going to fall lower. The average rate for somebody who is at rest, I think, is about 72. All right. So here is an example for what the derivatives are. I've already talked about this, but let's just mention it again. So if a function, here is the case of the function y is x squared. If we put in a value of x of 1, so if x is 1, which would be somewhere there, then the value of the function, that means the y value, we substitute it there, we expect it to be 1 because it's going to be f of 1 is 1, so that would be at 1. But the gradient function, if we want to find the gradient function, we will substitute into the gradient function if we want to find the gradient. So we substitute that into the gradient function, which we found as 2x, and we'll find that the gradient at the point where x equals 1, the gradient there is going to be 2. Similarly, at the point where x is 4, negative 4 for negative 2, for example, if we wanted to find the value of the function, we substitute in the function equation, and so f of negative 2 would give us That's negative 2. F of negative 2 should give us 4, which will come here as the function. But if we wanted to find the gradient at the point where x is 2, that's the gradient around there, then we have to substitute negative 2 into the gradient function, and that should give us negative 4. So that is supposed to be negative 4 there. So this gives us negative 4 for the gradient function, and so on. So this is how we make use of the derivative function. It helps us find the gradient. But eventually we will see how we make use of this in real life scenarios. All right? So the next line, I've just put a value of a, and I'm showing there how you can substitute it on the function to find the value of the function, and how you substitute it onto the gradient function or the derivative function to find the gradient at that point, at the point where x equals a. Yes? Next, let's have a historical note on the use of notation when it comes to differentiation or determining the derivative. All right? So the first notation here, dy by dx, was used by Leibniz, who was a German. The reason I want to talk about this is because this is about internationalism, and in the IB diploma we want to reason about internationalism. Why is it important to work in collaboration? How has collaboration helped mathematicians, and especially in the days when there were no computers and things like that, no mobile phones and so on, and these mathematicians were still able to communicate and work on mathematics ideas together. So Leibniz was the inventor of the notation dy by dx. He did this in Germany. The next one was actually a notation devised by Euler. This is supposed to be 17 here, not 10 or 7, but 17 or 7. This here is 1707. Okay, 1707 to 1783 was Euler. So he actually devised this formula, but this notation, but we normally attribute the notation to the Italian gentleman called Lagrange. Lagrange was an Italian, but was naturalized in France, and so he's a French Italian mathematician. So he merely popularized the notation, which was actually invented by Euler, who was a Swiss mathematician. So you can see that these were mathematicians all over Europe, but they were able to collaborate to come up with new findings or new knowledge in mathematics, right? Newton probably had the easiest notation to use there, which was just a y and a dot on top to indicate the first derivative. The second derivative would be 2 dots on top, and so on. Okay? I believe that brings us to the end of this lesson. In the next lesson, we will look at the next derivative, which is going to be x power 3, and then we will try to build it on from there for the sake of the HL students. Okay? Thank you, and see you in the lesson number 4.